LP Gaussian problem for Gaussian matrices, please.
Thanks, Ohad and Naomi, for the invitation. And I'm going to present a joint work with Weiko Chen. So let me start by describing what do we mean by LP Gaussian problem. So this is a simple optimization problem. So input is a n by n deterministic matrix A with vanishing diagonal entries. And the goal is to compute the maximum value of the quadratic form X transpose AX over the unit LP sphere. Okay. So here this vanishing diagonal assumption is not so important, and this can be dropped. So for at least for p equal to 2, we know that this is a very simple problem because this corresponds to the maximum eigenvalue of the corresponding symmetrized matrix A, right? So that can be computable in polynomial time. But for p bigger than 2, it is known that this LP Gaussian problem is NP hard. So this LP Gaussian problem is kind of well studied in the literature in the case when p is equal to infinity. So in that case, we are optimizing over n-dimensional discrete hypercube. Okay, and in this special case, this LP Gaussian problem or L infinity Gaussian problem is related to Gaussian inequality. So I am going to mention this Gaussian inequality, even though it will not come up later in my talk, but just for like exposition, I want to at least say what this Gaussian inequality is. I'm not going to tell you the most standard version of the Gaussian inequality, but I'm going to tell you a symmetric version, which is closer to our topic. So, so this is an inequality between two maximization problems. On the right-hand side, we have L infinity Gaussian problem. On the left-hand side, we have another maximization problem where we replace xi times xj with the inner product between two vectors vi and vj, where these vectors v1, v2, vn, these are unit vectors in Rn. Okay, so you can easily see that the left-hand side is bigger than or equal to the L infinity Gaussian problem, but the Gaussian inequality says that if we look at the optimization problem on the left-hand side divided by the optimization problem on the right-hand side, that is bounded above by some universal constant c times log n, okay, independent of the matrix A. Okay, so why do we care? Note that on the right-hand side, we have a integer optimization problem that is NP hard. On the left-hand side, it seems like we have a more kind of complex problem, but actually this is a convex optimization problem. So this can be polynomially computable. So we can think that the left-hand side is a SDP relaxation of the right-hand side, and this Gaussian inequality gives a approximation guarantee. Okay, so as an application of the Gaussian inequality, we can easily see that for the L infinity Gaussian problem, the optimal value can be approximated in polynomial time within a factor of log n. Okay, but on the other hand, there is no such polynomial time algorithm exist if we demand a approximation within a factor of log n to the power some sufficiently small constant. So this is a result by Cote and Sapra. When p is between 2 to infinity, things are a little bit better, but in this case, there is an inapproximation threshold, which is a constant strictly bigger than 1 that depends on p. Above that threshold, there is polynomial time algorithm. Below that threshold, there is no such polynomial time algorithm. And the case when P is between 1 to 2 is not explored in the literature as far as I know. And for P equal to 1, there is some indication that the problem is computationally hard. Okay, but we are probabilists, so we don't want to look at the worst case scenario. Actually, we want to study the random instance of this LP-Grothendieck problem, and the most natural input matrix will be just the n by n Gaussian matrix with IID Gaussian entries. Okay, so we for a general P between 1 to infinity, we look at the LP-Grothendieck problem for this Gaussian matrix, and we want to study its large n limit. So we want to understand the scaling. We want to find the limit. If it exists, we want to say something about the optimizers. Okay. Of course, the easy case, as always, is P equal to 2. In this case, this maximum value is just basically the top eigenvalue of the GOE, and it scales like 1 over square root n. Okay, so this is trivial. But the even for P equal to infinity, the problem becomes non-trivial, because now we are optimizing over the discrete hypercube, and this turns out to be the ground state energy of the Sherrington-Kirkpatrick spin-glass model. So I think many of you know what the Sherrington-Kirkpatrick spin-glass model is, but let me just tell you in a sentence. So it is a JIPS measure on the space of spin configurations, n-dimensional spin configurations, that takes the value plus or minus 1. And what is the probability of a spin configuration x? It is proportional to the e to the power some positive constant beta times the random Hamiltonian, and the random Hamiltonian is basically the quadratic form of the Gaussian matrix. Okay, so if we want to understand the low temperature behavior of this spin-glass model, actually we need to understand the ground state energy of the Hamiltonian, or in other words, we need to understand the maximum value of this Hamiltonian, and this is exactly the L-infinity Grothendieck problem. So this is a non-trivial result by Offinger and Chen, who used spin-glass techniques to prove that if we scale this maximum value by n to the power minus 3 over 2, so the scaling is different for P equal to 2 and P equal to infinity. P equal to 2, we had scaling n to the power minus half. Then it converges to some constant, and this constant is given by certain variational formula. Okay. So there are another variant which is also of the spin-glass model, which is also very well studied. That is called the Spherical Sk Model, where we have the same Hamiltonian, but instead of the discrete spin, we have continuous spin that sits on a L2 sphere of radius square root n. Okay, so similarly, we can consider spin-glass model with more general spin configuration space. For example, we can restrict the spins to lie on the suitable LP sphere, and in that case, the ground state energy will correspond to our LP-Grothendieck problem. Okay, so that's one of the motivation of studying this problem. Okay, so the first we need to understand how does this scale, how does the this maximum value scales, and how the exponent depends on P. So for that, I will mention this very classical Gaussian inequality, which is called the Sheaves Inequality. So it says the following: here we have an expected value of the maximization of a bilinear form of a Gaussian matrix, where we take the maximum over two bounded sets S and T. And Sheaves inequality says that it can be controlled by the two parameters of this set S and T. The first parameter is called the Gaussian width. So basically, this is the average of the maximum projection of a standard Gaussian vector onto the set. And the second parameter is the L2 radius of the set. Okay. So depending on these two parameters, we can control this expectation of the maximum from below and from above. So how does it relevant in our case? Well, in our case, we have maximum of the quadratic form over the unit LB ball. Okay. Now, so we can bound this quadratic form in terms of the maximum of the bilinear form, and then take the expectation and apply the Sheaves inequality. So to come up with the upper bound, we just need to compute what is the Gaussian width and the L2 radius of the unit LP ball. Okay. And that's a very easy computation. The Gaussian width scales like n to the power 1 over p star. And also the L2 radius is extremely simple to compute. When p is less than 2, the maximum L2 radius is achieved by the coordinate vectors. On the other hand, when p is bigger than or equal to 2, the maximum L2 radius is achieved by the vectors which is proportional to 1. So the vectors with constant entries. Okay. So we compute these parameters for the unit LP ball, and we plug that in the upper bound to obtain that the expected value of the LP Grothendieck problem can be bounded above by some constant times n to the power 1 over p star when p is between 1 to 2, and some constant times n to the power 3 over 2 minus 2 over p when p is between 2 to infinity. So one thing I should point out here is that this exponent is continuous at p equal to 2. Okay. So p equal to 2, it matches with half. And actually, the Sheaves gives us the right exponent because we can also find a matching lower bound by simple techniques. And for example, for p between 2 to infinity, we can obtain a matching lower bound just by taking the top eigenvector of the GOE and normalize it so that its LP norm is equal to 1. Okay, so this is how we kind of obtain the scaling. But of course, this does not give you the right constant. Okay, so before I tell you the main results, let me digress a little bit and mention a related problem. So this is P2Q operator norm of a Gaussian matrix Gn when P and Q is between 1 and infinity. And I'm a bit surprised to see that this problem has not been studied in the literature for general P and Q. Okay. So if we look at the operator norm, P2Q operator norm, we can use the dual representation of the operator norm and write it as the maximum of some bilinear form of the matrix Gn, where we take the maximization over the LP sphere and the LQ sphere. Okay, so this representation is tailor-made for applying the Sheaves inequality. So if I look at the expected operator norm of the Gaussian matrix, then as an upper bound, we get a linear combination of two different powers of n. And as a lower bound, we have the same quantity almost, but instead of the sum, we have max. Okay. So this already tells me the right scale of the operator norm of Gn. because the scaling exponent will be the maximum of these two exponents. Okay, and moreover, when these exponents are unequal, actually we can pin down the limiting constant. Okay, so the simple Sheaves inequality actually gives us the limiting constant when these exponents are unequal. But of course, the more interesting case is perhaps when we have equalities for the exponent, and in that case, the Sheaves inequality is not strong enough to kind of imply convergence, let alone the limiting constant. So this equality holds in two cases: when p is between 2 to infinity and q is between 1 to 2. Okay, and the another case is when the q is basically the Holder conjugate of p. So let me mention that in the second case, when q is equal to p star, we are basically looking at the p to p star operator norm of the matrix Gn. So these we can write as the maximum of the bilinear form, where we maximize x and y both belonging to the unit LP ball. So this is related to the ground state energy of the bipartite spin glass model, and this bipartite spin glass model is much harder to analyze compared to the ordinary mean field symmetric spin glass model. So it seems like this is a hard problem to kind of show convergence or to find the limiting constant. Okay, so let me mention that last year there was a paper by Dhara, Mukherjee, and Ramanan who studied this P to Q operator norm of a n by n symmetric random matrix with IID non-negative entries. Like think of adjacency matrix of a Roshini random graph. Okay, and as a consequence of their results, they can show that if we look at the LP grothendieck problem for this matrix AN for p bigger than 2, the maximum value has a Gaussian fluctuation. But their method actually heavily depends on the assumption the entries are non-negative and cannot be applied for the Gaussian case. So
I'm sorry, I think we missed some point. Is 2 contained in 1? Is 2 some specific case of 1?
Yeah, so these two cases are not disjoint.
But isn't one always containing the other? Could you have P equal Q equal P star and not have one of them between 2 and infinity and the other between 1 and 2?
So what happened now? So in the 1 we have P bigger than 2.
Okay, it matters, but there is symmetry in the equality, right? So can't you take the? I see. No, there's no symmetry in the star. I see. Okay. Yes. Sorry.
Yeah. So these two cases are not disjoint. Yes. Okay. So so let me now come back to our LP grothendieck problem and start describing the results. So first is the easy case when p equal to 1. In this case, we are of course optimizing over the L1 ball or L1 sphere, and the maximum value of the quadratic form is roughly like square root 2 log n. And if you see the square root 2 log n, you can probably guess that this is basically the maximum of n IID diagonal entries. Okay, so one can also show that any near maximizers or near optimizers lies close to one of the coordinate vectors, where the coordinate I is such that the corresponding diagonal entry of the matrix is close to the maximum of the n diagonal entries. Okay. And of course, this each near optimizer is localized because this is close to the coordinate vectors. So this is an easy result, and it's probably an exercise. Okay, so so let's now move to the case when p is bigger than 1. So here, actually, the results are completely different when p is less than 2 and when p is bigger than 2. So let me divide this into 2 separate cases and first tell you what happens when p is between 1 to 2. So in this case, note that we have to scale it by n to the power 1 over p star. So after rescaling, the maximum value converges to a simple constant depending on p that involves, let's say, the p star norm of standard Gaussian. Okay, so this is a simple object. So not only we can just describe the limit, but we can also describe, we can give a complete description of the near optimizer. So for that, I need to define this set O. So ignoring the signs, which are basically trivial, this set O contains n vectors. So for each I have the ith coordinate vector. Then I add some vector vi, which I'm going to describe in a second. And then I normalize so that it sits on the unit LP sphere. Okay. And I claim that any near optimizer has to be closed to this set O. So that I'm going to describe in the next slide. But let me first tell you what is this vector vi. So vi is as follows. So vi is the vector with.
Should it be vi in the denominator? So is it ei plus vi?
Yeah, sorry. Yes. Sorry.
Okay.
This is a typo. Thanks. So vi is the vector with the unit LP norm that maximizes the correlation with the ith column of the GOE. Okay. In other words, if we take the correlation inner product between vi and the ith column of the GOE, we get the p star norm of the ith column of the GOE. And of course, this follows from the Holder inequality. And if we chase when the identity occurs in the Holder inequality, actually we can give a formula for the vi. And it turns out that this vi is very flat. So vi is a vector in LP, and each of the entries is roughly of the order of 1 over n to the power 1 over p. Okay. So so what is the result? The result is, if we take any vector in our set O, then asymptotically it achieves the limiting constant. Okay, so that means that each vector in our set O is a near optimizer for our problem. And not only that, our next result says that if we move a bit away from the set O, let's say in LP distance, okay, then the value of the quadratic form actually drops below the maximum value. Okay, so in other words, any near optimizers lies close to this set O in LP distance. So so what do we get here? That so basically there are linearly many near optimizers in this problem, and this near optimizers has both localized and delocalized component, because if we look at this vector ei, so there is a single spike at the coordinate I, which is of order 1, and rest of the coordinate we only have dust. Okay, so this is the description of the near optimizers in this problem. Any question? Okay, now we move to the next case when p is bigger than 2, and this is for us more difficult case.
So when it approaches 2, what happens? Just to get a good image, the dust becomes bigger and bigger. How should I imagine it when p is approaching 2 from below? What will be the change to this dust component?
So I think like you will just have like I think the problem has a discontinuity at p equal to 2. So I don't think you will achieve like, of course, when p equal to 2, the optimizer is basically the top eigenvector of GOE, which is basically all dust. So, but for any p, you can see that you always have a spike in the near optimizer. So,
but isn't the spike becoming smaller the way it's in here because the dust becomes stronger and stronger and stronger? It will, yeah.
For a fixed p, I think you always see a constant spike. But I have to think like if you let p also varies within that, I am not sure. I have to think for a second. Okay, so let me continue with we can continue this discussion later actually. So let me tell you what happens when p bigger than 2, and in this case, let me first tell you the result that guarantees the actually the limit exists, because that is also not so trivial to prove. Okay, so note that now that p is bigger than 2, we use the different exponent. So if we look at the rescaled LP Grothendieck problem, and so here we are maximizing over the standard L2 sphere, but instead of this standard L2 norm, we move to the standard LP norm, we move to this normalized LP norm. So one reason for doing that is that the expression looks much cleaner now. So we now have a scaling n to the power 3/2, which we found also for the case p equal to infinity. But of course, I mean, this doesn't solve the problem. The problem remains that this LP constraint is difficult to deal with. So what we do, we use the idea of the Lagrange multiplier. So we remove this constraint and put it back as an external field, where t, this parameter t, serves the role of the Lagrange multiplier. So we define this Lagrange function where we have this unrestricted maximum over Ra. So this unrestricted maximum makes sense because in the external field, it goes like power p is bigger than 2, which dominates the interaction term, which is only quadratic. Okay, so actually, let me kind of go to the last bullet point and then come back here. So actually, this Lagrange function is connected to the rescaled Grothendieck problem via this identity. And this identity holds true for every t. Okay, so this is basically at the very simple form, this is just the calculus of Lagrange multiplier at a very high level. Okay, so if we want to prove the limit of the left-hand side, we just want to prove this Lagrangian function converges. Okay, it turns out that proving directly it converges is difficult. So we introduced and restricted Lagrange function where we introduce the additional restriction that the normalized L2 norm square of x is equal to u. Now it seems like we are going back circle because we first remove this restriction and then we are putting back another restriction. But note that this restriction is a LP constraint, whereas the new restriction is a L2 constraint, which is much easier to deal with. And actually, in the language of spin glass, we are basically demanding that the self-overlap of the spin x is equal to u. So what is the advantage of this? restricted Lagrange function? Well, for this restricted Lagrange function, if we look at the new function n times the expected value of this, we can prove super additivity by using Guerra-Toninoli's interpolation scheme. And from that, actually, it follows that the limit of this restricted Lagrangian function exists. Okay, but we want to get the limit of the unrestricted Lagrangian function. Of course, the unrestricted Lagrangian function can be recovered from the restricted Lagrangian function by taking supremum over all u. So if I want the limit of the unrestricted Lagrangian function, we first take the supremum and then take the limit. But actually, we can reverse the order of the supremum and the limit by a compactness argument. So for the restricted Lagrangian function, we already know by subadditivity this converges. So so that we get that also the unrestricted Lagrangian function converges to some deterministic function, which is basically supremum of the limit of the restricted Lagrangian function. Okay. And that actually proves the convergent existence of the limit. So one thing I should mention here, that even though the right hand side is a function of t here, the left hand side doesn't depend on t. So this holds for every t. So there is this auxiliary parameter t here. Okay. So any question on this slide? Okay. So what about the optimizers? So we can prove the following partial result for the optimizer. So if x star is the maximizer of our LP Gaussian problem for p bigger than 2, then and let's say x star LP norm of x star is 1, then we can show that the L infinity norms of x star decays like n to the power some small positive power. Okay, so what we get here is not optimal, and we believe that actually the optimizer is fully delocalized. So what we proved is a weak delocalization result, but actually we believe that the optimizer is fully delocalized, so that up to some polylog n correction, the L infinity norm should look like 1 over n to the power 1 over p. Okay, and so we also conjectured that the energy landscape, the quadratic form of the Gaussian matrix, should look like the energy landscape of the Sk model. Okay, so in other words, with high probability, there should be exponentially many near optimizers that are approximately orthogonal to each other. For Sk model, this was a result by Chen, Hansi, and Larman from 2018. But at this moment, we don't have control on the near optimizers of this problem when p is bigger than 2. Okay, so we can only handle the true optimizer, and we can say that it is weakly delocalized.
So when you say fully delocalized, what do you mean?
What I mean is basically it behaves like a constant vector up to polylog n correction. So if you have a constant vector which has a unit LP norm, then each entry will be 1 over n to the power 1 per p. By fully delocalized, I mean that up to some polylog n, this x star behaves like that.
But it doesn't prevent a shape theorem in principle, or does it? That it could still belong to a very small set in this space. But it's not that it's like the optimizer is a random vector, is it?
No, I'm not saying that. Yeah,
I
right.
see.
I mean,
It's
you
a
are
weaker,
right.
it's
I
a
mean,
weaker statement, right? It is,
yeah,
it
it's
is
like what you were
spread
saying
out on a large
yeah.
set.
Yeah, so what you are saying is kind of the quantum erodicity, perhaps. But yeah, that might be true, but that's
so do you expect it to be true, or this sounds maybe very surprising? This is why I'm asking.
I don't have any kind of guess like that. That's quite a strong statement, and I don't have a guess.
Okay.
Yeah.
So.
Okay. So finally, let me give you a description of the limit. So again, coming back to a previous slide, so the limit can be expressed in terms of the limit of the Lagrangian function. And this limit of the Lagrangian function can be expressed as the supremum of the limit of the restricted Lagrangian function. So all I have to do is to give you a description what is the limit of this restricted Lagrangian function. Okay, so this restricted Lagrangian function has a description involving a parity-type formula, some variational problem. So if you have not seen any parity-type formula before, this slide might look a bit overwhelming, but I just want to give you a sense of what kind of goes on, goes into these kind of formulas. Okay, so this is the limit of the restricted Lagrangian function. This is infimum of a functional, and infimum is over two parameters, lambda and gamma. Lambda is a real number. Gamma is a positive measure on the interval 0 to u, such that gamma is atomic with finitely many atoms. Okay, and what is this functional? Well, this functional depends on t and u, which is fixed. It has three terms. The second and third terms are linear, so these are harmless terms. The first term is a complicated term, which is a solution to a parabolic PDE given by this equation. So this is a PDE which is defined on a strip 0u cross r, and on the right boundary we have this boundary condition. So note that P enters only in this boundary condition, nothing else. Okay, so this is a kind of a complicated description of the limiting constant. Okay, so this is, I mean, it's kind of hard to absorb all these details in a minute, but I just want to give you a flavor of the things involved. Okay, so let me just tell you a quick thing that, as I said, there is a phase transition at p equal to 2. So if I look at the limit as a function of p, then we see that the limit is continuous between the open interval 1 to 2, and also it is continuous within the on the closed interval 2 to infinity. But what we can find is that this limit has a jump discontinuity at p equal to 2. Okay, so the limit is right, is a right continuous at 2. Okay, so maybe we can I can pause for a second for questions, because now I want to give you the spoof sketch when p is between 1 to 2. Okay, so when p is between 1 to 2, actually the proof doesn't involve spin-glass techniques, and the proof is actually quite simple. It involves fairly soft argument. So we start by decomposing the vector x as x naught and x plus, where x naught actually carries all the entries of x that has a magnitude less than or equal to epsilon, and x plus carries all the entries of x that has magnitude bigger than epsilon. And epsilon is some threshold which we let to 0 as n tends to infinity. Okay.
Why square root of 2? Why square root of 2?
The square root of 2 appears because this Gn bar, which is the GOA matrix, is defined as Gn plus Gn transpose over square root of 2.
Thank you.
Okay. So now we have this quadratic form. Then we can write this quadratic form as the two quadratic forms involving the x naught and x plus, and then we have a cross term. Okay, and now we can use the Sheaves inequality to say that uniformly in x belonging to the unit LP sphere, both these diagonal terms are small. Okay, the first diagonal term is small because x naught is a delocalized vector, and as such its L2 norm, sorry, L2 radius of the corresponding set is small. The second diagonal term is small because x plus only carries the localized component, only carries few spikes. So it has this set of x plus has low cardinality, which means that its Gaussian width is also small. Okay, so so basically, if we want to compute the expected value of the maximum of the quadratic form, we have to basically estimate the expected value of the maximum of this cross term. Okay, so anyway, one thing I am always computing this expected value, but one can just use the Gaussian concentration to go from the expectation to the original value. Okay, so how do you compute the expected value of this maximization of the cross term? So first we do a trivial thing. We just normalize the both vectors so that their LP norm becomes 1. Then we look at this green vector. So for every choice of x plus, we can choose this unit vector, the unit vector with unit LP norm, such a way that maximizes the inner product. And then we get the P star norm of this blue vector. Okay. Now we have the product of these two norms. Of course, the product is maximized if the norms are actually equal, their values are equal. So from that, we also get another inequality. And now we have to have an expectation of the maximization over the unit LP ball of this blue vector, the P star norm of this blue vector. But note that here, this LP normalized x plus has low complexity because it has only few non-zero entries. So we can use the concentration, Gaussian concentration and union bound to kind of commute the maximization and the expectation. And we can take this expectation outside the maximization max outside of the expectation. Okay.
What is low complexity?
So low complexity means here this we can find a delta net. So if I want to approximate this this set with a delta net, I forget the exact estimate, but for the full LP ball or LP sphere, we need a the size of the delta net is much larger, but in this case, the size of the delta net should be much smaller because there are only a few coordinates where which can be non-zero at a time. Okay.
Thank you.
Okay, so so now this expectation is easy to compute because we are just computing, so there is no maximization involved inside the expectation. So we are basically looking at the GOE times Y, the P-star norm of that and expectation. So the Y enters into the picture only through its L2 norm because of the rotational invariance of the GOE. Okay, so basically we are left with this LP normalized X plus, the L2 norm of that, and then we take the maximum of this L2 norm over the unit LP sphere. And one can easily check that here the maximum is achieved if X plus is some constant times one of the coordinate vectors. So if you plug in that, then basically we get the desired upper bound. Okay, and now not only this gives the upper bound, it also tells us how do we find the lower bound and what will be the near optimizer. So basically in this upper bound, we have always used equality except for the three places. In the first place is where we use X plus should be a constant times and one of the coordinate vectors. The second place is when we demand that the LP norm of X naught and X plus, they are same. And the third place is in this maximization, because now note that by our choice, this becomes EI, right? So what is the choice of X naught that maximizes this inner product? The choice of X naught or the normalized X naught should be exactly equal to VI, like we described. Okay, so this gives us the near optimizers as well, and we can do a rigidity analysis on these inequalities to kind of say that these are the only near optimizers. Okay. So I'm probably almost running out of time. So I will kind of make a brief comment for the case P equal to 2. So this Parisi formula. So in this case, note that we work with this restricted Lagrangian function. So this is the maximum over a L2 constraint of this Hamiltonian over n. Okay. To get a handle on this Hamiltonian, the natural thing is to look at is the free energy. Okay, so we look at the free energy. We look at e to the power beta times the Hamiltonian. We integrate over the surface measure on the sphere, take the log and divide it by beta times n. And then if we fix n and let beta tends to infinity, we get back the maximum value, which is the restricted Lagrangian function. But what we want is basically we want to fix beta and first let n tends to infinity. So in the spin dust literature, we generally have a formula for the limiting free energy given by some Parisi formula, and that Parisi formula involves beta. And then we let beta tends to infinity in that Parisi formula and do some delicate analysis to come up with a formula for beta equal to infinity. In this case, the things are more complicated because we don't have a Parisi formula for this object. So for that, we kind of come up with both upper and lower bound for this limiting Lagrangian function, and analyze the upper and lower bound separately and prove that miraculously they match. So for the upper bound, instead of looking at this free energy, we look at a slightly different free energy where instead of the square of the normalized L2 norm of X equal to U, we take the the square belonging to u minus epsilon to u plus epsilon for some small fixed parameter epsilon, and define the free energy. And this blue free energy actually comes up in the upper bound. So in this blue free energy, if we let n tends to infinity and then let beta tends to infinity, simultaneously letting epsilon goes to 0 as beta tends to infinity as read 1 over beta square or 1 over beta cube, then we get an upper bound for this object. Okay, and this can be studied by Guerra's replica symmetric bound. For the lower bound, things are more complicated. In this case, we have a new free energy, which is the red free energy, where we put an additional constraint that the spins are all the spins are inside some large box of fixed width. Okay, a fixed width 2m, and then we perform various limit. First, we let n tends to infinity, then we let epsilon tends to 0. So this is not done by us. This was a previous work by Dmitry Panchenko, who actually proved that if we take these two limits, there is a Parisi formula. So what we did is we take the limit beta tends to infinity in that Parisi formula, and the more technically challenging step was after taking the beta tends to infinity limit, we have to take the m tends to infinity limit. But somehow we could manage that taking the limit, and miraculously the lower bound matches with the upper bound. So it's very hard to kind of give all the details here, but this is how the proof goes. So maybe let me conclude by stating a few more open problems. So of course, a natural question, what about the fluctuation? So we haven't studied that in our paper. So there are two questions here. One is what is the order of the fluctuation, and the second is what is the limiting distribution. Okay. We believe when p is between 2 to infinity, the fluctuation is Gaussian. But yeah, it will be kind of hard thing to show. In the second open problem, so in our proof, we use the Gaussianity of the entries quite a lot. So a natural question will be, what happens if we have other entry distribution? For example, take the plus minus 1 IID random variables. And one should expect universality when p is between 2 to infinity. Of course, I cannot expect universality probably for p is less than 2, because when p is less than 2, the limiting constant depends on the p-star norm of the standard Gaussian. So that depends on the distribution of the Gaussian. And finally, there is this algorithmic question. So again, let p is between 2 to infinity. Is there a polynomial time algorithm that outputs a near optimizer of the LP-Grothendieck problem with high probability? Okay, so so why we are asking such a question? Because of course, for p less than 2, such a question is trivial by our results, because we know the explicit description of the near optimizer set. But for p bigger than 2, there should be exponentially many near optimizers, and we don't have any description. So this is a natural question to ask. For p equal to infinity, the Sk model, the answer is yes. And this is done via the approximate message passing algorithm, so which was developed by Montanari and his co-authors, building on earlier work by Shuba. So hopefully such similar algorithm should also probably work in the p bigger than 2 case. Okay, so I'm running out of time, so let me stop here. And the paper is on the archive. Thanks for your attention.
Let's thank Arnab. Questions for Arnab? So let me ask, did you see simulations of this? So how does the maximizer look on a sample in some dimension?
So if you, I mean, yeah, that's a kind of a difficult thing to simulate, because that's probably this question here, right? I mean, how do I find
even in relatively low n, it's the
probably
thing is,
that can be done, yeah, for relatively low n, but still it's exponential in n, the naive algorithm.
So somehow, right, when p is less than 2, the shape is a bit like a simplex with some reflected visual version of a simplex, and you say that the optimizers are happening near the corners, right? That's more or less the situation.
When
and
p,
when p is next to infinity,
when p is equal to less than 2 is, I think like we have something like this with a single large entry, and everything else is dust.
right? By symmetry, you can think of it as if you had the unit ball, and in each cardinal direction, you have a corner of the unit ball, and you want to take one of these corners.
Right.
Right?
Mm-hmm.
When p is near infinity, the unit ball is like a cube, and it was natural to think that you'll go towards the corners. Right? There are many more corners now. There are exponentially many corners.
Right.
Right.
But
so the question is,
mean,
how much is it the case, or is the entropy of the entire shape make it go away from the corner? That's somehow what I'm not completely catching from this result.
So basically, I mean, let me tell you that even for p equal, so let's consider the p equal to infinity case. So all you have is corners, right?
Right.
So there, the non-trivial result is you can get exponentially many vectors near optimizers which are nearly orthogonal to each other. So basically, you have exponentially many well-separated peaks in the energy landscape.
Okay. Shall we thank Arnab again? Thank you.
And Arnab, maybe, sorry, another question. Could you say again what you think happens to the fluctuations? That's interesting. Will there be a different behavior for p less than 2 and p bigger than 2? I imagine.
So okay, so let me say a few words. So for p, actually we haven't studied that in detail. So and we haven't thought about that too much. But for p less than 2, we already have an explicit description of the near optimizer. Okay. So so actually, like we are not sure whether this kind of, so of course this is the near optimizer, it is not the true optimizer, and we are not sure that if we plug in the instead of the taking the maximum over the entire LP sphere, if we just take the maximum over this near optimizer, which is just linearly many terms, the error will be smaller than the fluctuation order. If we have that, then we can just study, like we can forget that we have a infinite maximization problem. We can just take the maximum over these linearly many terms and just study the corresponding object.
Right.
So we don't know whether this kind of near optimizers are kind of strong enough, in the sense like maybe we need some other. This is the leading order term, but probably we need other correction terms here.
But you don't know that the maximum, you also know that the maximizer itself is taken from this set O, not just near the maximizer itself. So if you maximize only over O, then you're okay, right?
Yeah, but the maximizer, the exact maximizer is close to O, but it's not exactly, may not.
It's not exactly in O.
Yeah. And what, so for P bigger than 2, what happens is that.
And this, and if it was in O, then it would lead to some Gaussian behavior, probably. Or you don't know.
No, but it will involve this P-star norms and etc.
So it might still be complicated. Oh.
Yeah, but it's something that can be described. It's not like a very complicated.
I can imagine.
Yeah. So when P is bigger than 2, so we have this connection that so not only we have a connection in the limit, but we have a connection in the finite n. So this is the Lagrangian function, and this is our rescaled Rothendick problem, right? So to show that maybe to show that this the left hand side is Gaussian, has Gaussian fluctuation, all we need to show this Lagrangian function have Gaussian fluctuation. So this is basically the fluctuation of the Sk model in terms of a strong external field. The fluctuation of the ground state energy of the Sk model in terms of the strong external field. So this kind of external field has not been studied, but it has been shown for the Sk model with a external field, generally the ground state energy, like other more like analyzable external field, the ground state energy has Gaussian fluctuation.
Very nice. Thanks a lot. Very interesting.
Thank you. Maybe I should stop the share so that I can see the faces.
Okay, yes. Maybe we can also stop the recording if you want. Or